Okay, so now after watching all of the videos up to this point, you know everything there is to know about the hydrogen atom, its energies, its properties, what different physical effects or physical interactions change its energy, and so on. But it turns out there's 116 something other elements in the periodic table, and we haven't touched on those at all, and the class is ending. There's a really simple reason for that, and the really simple reason is that it's hard. So as soon as you have more than one electron, everything gets a little bit harder. And so in this last video, I want to take just a couple minutes to explain why that is, and also to give you an idea of the consequences of that extra interaction, or the consequences of the electron-electron interaction on both the physical properties and on the way that we have to solve the equation. So let's start by writing out in a really hand-wavy way the electronic Hamiltonian that corresponds to the helium atom, right? So we're not going crazy. We're not going to pick up uranium. We're just going to go to the next biggest atom that has just one more electron. Okay, so helium atom has 2 electrons, and still we're just going to consider this as having 1 nucleus, but it will have a charge that's equal to +2, right? So it's still just 1 nucleus. So the Hamiltonian that corresponds to this, and this is just the electronic Hamiltonian. We're not going to include any of the more complicated things like spin orbit, because as we'll see in a second, this is already too hard for us to do analytically exactly. Okay, so all of the terms that go into the Hamiltonian for the helium atom will be, first, it'll be the kinetic energy of the nuclei, which I'm writing as T hat N, so the capital N indicates this is for the nuclei. Then you have the kinetic energy of electron 1. You have the kinetic energy of electron 2, and so each of these will be the normal minus h bar squared nabla squared, but the derivative will only be with respect to the position of electron 1 or only with respect to the position of electron 2. Okay, and then we need to include the potential energy of this. So all of the potential energy terms will have the same factor in front. This will be E squared over 4 pi epsilon 0. And now times a big term. So the first term that you'll see is the Coulomb attraction between electron 1 and the nucleus. So this will have a negative sign because it's an attraction. Has a factor of 2 up top because there's a charge of 2 in the nucleus. And then it decays as R minus R1. Where this big R is the position of the nucleus and R1 is the position of the electron 1. You have the same interaction that corresponds to electron 2. So this will be 2 divided by magnitude of R minus R2. And now what makes this complicated is this last term, which is the electron-electron repulsion term. So this is a positive term, has a plus, and it's 1 over R minus R2. Okay, so all 3 of these are Coulomb terms. These 2 are attractive because they have the electron and the protons have opposite signs. And then this one is repulsive because the electrons have the same sign. This equation, as is, it turns out, cannot be solved exactly. One of the complications is that this is now a 3-body interaction, and so you cannot simply change variables and remove the nuclear kinetic energy of the proton, or of the nuclei in this case. But just because this is so much heavier than the electrons, we can actually, to a pretty decent approximation, just wipe this out. This is equivalent to assuming that the helium nucleus is just fixed in the middle of space and it doesn't move, and we don't really worry about the quantum nature of the helium atom itself. And this could be a really good approximation in a lot of different regimes. And so if we take a look at what that does, we can just wipe this out. And here's what we're left with. Okay, and this makes it a lot simpler, but it turns out that even this is too complicated to solve exactly analytically by hand. And the real culprit is this little bugger right here. So this electron-electron repulsion term. If this weren't here, then what you'd have is basically two independent hydrogen-like electrons. But because these two things interact, it couples the two equations. And as a result, you cannot solve it exactly by hand. Instead, you have people like me whose entire job is to be able to solve more complicated electronic problems using computers. There's actually a second, more important consequence of this electron-electron repulsion term. And that has to do with the structure of the periodic table itself. So one thing that many of you may have found confusing so far is that we've been saying that, with the exception of these minor differences arising from spin-orbit interactions or magnetic field effects, the energy levels depend only on the principal quantum number, the n, and not on L at all. And so this says that, for example, for n equals 2, it says that the 2s energies are the same as the 2p energies. This really actually flies in the face of our experience when we think about the structure of the periodic table. We learn about the structure of the periodic table in terms of the s, p, d, and so on orbitals. And when we're doing that, it sort of naturally pops out from that analysis that the s orbitals inside of a shell will get filled first, and then the p orbitals, and then typically much later the d orbitals, right? But the solutions to the hydrogen atom have all of those with the same energy. So the 3s, the 3p, and the 3d all have the same exact energy, even though they are filled in very different orders. Okay, and it turns out that that is a consequence actually of the electron-electron repulsion. Right, so without the electron-electron repulsion, the electrons only feel a Coulomb potential, a pure Coulomb potential, just with the nucleus. And that has this special property that the energy will only depend on the principal quantum number. But with the electron-electron repulsion, because these other electrons now effectively screen the electrons that are further away from the nucleus, that effect, that screening effect, gives a lower energy to the electrons that can burrow closer to the nucleus, like the s electrons, and effectively pushes up the energy for the states that cannot burrow close to the nucleus. Okay, and so this is the origin of the actual structure of the periodic table. Okay, and that concludes the chapter for the hydrogen atom.